I've been asked to solve this equation for x, an element of 0 to 2 pi. But what I'm going to do first is find all solutions and then generate the solutions that fall within 0 to 2 pi. The first thing I notice on this problem is that we have a sine squared here and a cosine. So even if I move the 1 over to the other side and set it equal to 0, I wouldn't be able to use the quadratic factoring method that we've used before because these trig functions are not the same. So we do need to use a trig identity to get rid of one of these. Now, the trig identity that should come to mind first, pretty much always, is sine squared plus cosine squared of x is equal to 1. And we can solve for sine squared by subtracting cosine squared of x from both sides. And we get sine squared of x is equal to 1 minus cosine squared of x. And now we can take this and plug it into the equation where the sine squared is. So doing that, we'll need to remember that this 2 is multiplied by everything that sine squared is. So both the 1 and the negative cosine x have to be, cosine squared x have to be multiplied by 2. So we'll distribute this 2 to both terms. We get 2 minus 2 cosine squared of x minus cosine of x is equal to 1. Setting this equal to 0 now, we would subtract 1 from both sides, and we get a negative 2 cosine squared of x minus cosine of x plus 1 is equal to 0. I just reorganized it so that I could have my quadratic term first, my linear term second, and my constant term third. So that if I wanted to use the quadratic formula, I could. But first I want to see if this will factor. I'm going to multiply through by a negative 1 so that my cosine squared term is positive. 2 cosine squared of x plus cosine of x minus 1 equals 0. So my goal is to create two factors, linear with cosine. So I'm going to try 2 cosine of x and cosine of x. And 1 factors into 1 times 1. Since this is negative, one of them is going to be positive and one of them is going to be negative. And since my middle term is positive, I want the larger term, the 2 cosine x times the 1, to give me a positive, and then I can subtract off a negative cosine of x. And so now I know my middle term will factor correctly. Now, since I have these 2 linear factors in cosine, either this term has to equal 0 or this term has to equal 0, or the entire equation won't work. So I split down the middle and I set both of these equal to 0. 2 cosine of x minus 1 equals 0, or the cosine of x plus 1 equals 0. To do this, I get 2 cosine of x is equal to a positive 1 because I added 1 to both sides. If I divide by 2, I get the cosine of x is equal to 1/2. On this side, I get the cosine of x is equal to negative 1 because I subtract 1 from both sides. If we draw a unit circle, the cosine equation is represented on the unit circle by the x coordinate. So this is the line x equals 1/2. That means we're going to get this angle when we take the inverse cosine of both sides. So, and since this is a nice ratio for the cosine, I know that the x coordinate is 1/2 and the y coordinate is square root of 3 over 2, based on what we know about the unit circle. So the principal solution comes from when we take the inverse cosine from both sides. Now, this is the single solution that the inverse cosine will give you when you take the inverse cosine of 1/2. But the cosine of x is equal to 1/2 at every point that is coterminal with this angle too. So we'll add plus 2 pi k, where k is the number of revolutions and the direction of revolutions you go to get other coterminal angles here. If k is positive, then we will go in the positive direction and add 2 pi to it. If k was a positive 2, then we'd add 2 pi's to it. So that would mean we'd go around twice. And k is an integer. And this is shorthand for saying k is the set of all integers. So this is one possible solution. And remember, this line right here, x equals 1/2, intersects the circle in 2 places. We get this second angle here, which we can describe as the negative angle or as its positive angle. I'm going to describe it as its positive angle. So here we get x is equal to 2 pi minus the inverse cosine of 1/2 plus all of its coterminal angles, so 2 pi k. Now, since the inverse cosine is taken of 1/2, and this is a nice ratio, we know that this is the angle pi over 3. And that means this angle right here is pi over 3 shy of 2 pi. So that angle was 2 pi minus pi over 3. And since 2 pi is 6 pi over 3 minus pi over 3, our second angle is equal to 5 pi over 3. And so we'll get any angle that is coterminal with 5 pi over 3 will give us a solution. And any angle that is coterminal with pi over 3 will give us a solution. So we can rewrite these as x is equal to pi over 3 plus 2 pi k, or x is equal to 5 pi over 3 plus 2 pi k. Now we don't want to forget about this equation up here that we have to solve. The cosine is equal to -1 only once on the unit circle, because that's the only place where the line x is equal to -1 intersects the circle. So we also get x is equal to the inverse cosine of -1 plus 2 pi k, so all of its coterminal angles. And this happens to be the angle pi. So this is equal to pi plus 2 pi k. Pi plus 2 pi k. So now all of these angles here are positive angles. And so for the k equals 1 solution, k equals 0 solutions, we get x is equal to pi over 3, 5 pi over 3, and pi. All of these are elements of 0 to 2 pi. If k was equal to 1, we would get the solutions x is equal to pi over 3 plus 2 pi, 5 pi over 3 plus 2 pi, and pi plus 2 pi. All of these are greater than 2 pi. So these will not be included in the solution for the initial problem. These here, the k equals 0 values, are on the given domain. So we can now conclude that if we have 2 sine squared of x minus the cosine of x is equal to 1, this equation is true whenever x is equal to pi over 3, 5 pi over 3, and pi, for x values on the domain 0 to 2 pi.